So now we're moving on to talk about the determinant of a matrix. And we're going to start with the 2 by 2 because everything's kind of built off this idea of a 2 by 2. So when we talk about the determinant of a 2 by 2 matrix, it's just when we multiply these terms minus these terms. And we kind of mentioned this idea when we talked about inverses. If we have a 2 by 2 that can be written this way, A, B, C, D, then the determinant of that matrix, I'm going to call it matrix A, is AD minus BC. And that determinant kind of played a role when we talked about the inverse of the matrix. We said that the shortcut for a 2 by 2 is 1 over that AD minus BC, which is 1 over the determinant times this matrix. So that determinant plays a role in that. And we'll see other uses for determinants later on. You actually saw some back in 171, if you guys remember the cross product. The cross product happens when you take two vectors and you put ijk across the top. I'll call it v1, v2, v3, and then w1, w2, w3. So that cross product was actually a determinant. And remember, that produced another vector that was orthogonal to both of those two vectors in space. So we've seen this idea before, but now we're going to branch it out past what a 2 by 2 looks like, past what a 3 by 3 looks like. And then the question becomes, well, how do you find that? How do you find that kind of determinant? So let's talk about that. So when we talk about determinants of anything that's bigger than a 2 by 2, we get into this idea of minors and cofactors. So to find a determinant, first off, you have to have a square matrix. Determinants of non-square matrices just don't exist. So we have to have a square matrix. The minor of a particular entry is determined by deleting that row and that column. So let's say we want to find the minor of A21. A21 is in the second row, first column. So here's your second row, first column entry. So if we were to do what's called an expansion, we would delete this column, delete this row. Notice that these are the entries that's left. That becomes your minor. And notice the notation they're using here. They are not using the brackets. They are using what looks like absolute value. That's your notation for, I need to find the determinant of whatever is inside there. So your minor that corresponds to entry A21 deletes that row and that column that entry lives in, and the minor is just whatever's left over. So if we want to find the minor of A22, A22 is the guy that's right in the middle. So I'm going to delete that column and that row. The entries that are left over are A11, A13, A31, and A33. So those make up your minor. So if we want to throw one in, let's say we want to throw one in with numbers. So suppose we have matrix A as this guy. And let's say we want to find the minor for A32. So A32 is in the third row, second column. So here's A32. If I were to take that row out and take that column out, then the minor for A32 would be the numbers that are left over. So I've got 1, 4 left over in a column, and I've got 3, 6 left over in a column. So there's the minor that would correspond. The cofactor just includes the 1 in front of it, whether it's a positive or a negative 1. So cofactors are found by taking negative 1 to the I plus j column times that minor. So going back to that first example over here, a really generic example. So we're looking at the A21 entry. We want the minor of A21. We already found the minor. Now let's find the cofactor. It's just going to include that minor, but we need to take this negative 1 to the 2 plus 1. Why is it 2 plus 1? Well, because it's in the second row and it's in the first column. So you use those subscripts to come up with that exponent. It's always going to be negative 1 to some power. So this is going to be negative 1 to the third power, and negative 1 to the third power is still a negative. So our cofactor that corresponds to the A21 entry is going to be the negative of that minor. If we go to the minor of A22, same kind of concept. We have negative 1 to some power. This is in the A22 second row, second column. So it's going to be negative 1 to the 2 plus 2. Well, 2 plus 2 is 4. Negative 1 to the fourth is a positive, so it's just going to be M22. If we go back to our example up here, let's say we want to find the cofactor for that A32. It's going to be negative 1 to the 3 plus 2 times that minor that we just found. So we're going to have negative 1 to the fifth, which is a negative 1. And just so you can see what it would look like when we write that out, we have the negative of 1, 3, 4, 6. So then we could find that determinant and then find that value. So now let's move on to this definition. So if A is a square matrix of order n greater than or equal to 2, then the determinant of A is the sum of the entries in the first row of A multiplied by their respective cofactors. So this is called a cofactor expansion. So if we want to find the determinant of a matrix, so 2 by 2s are easy, right? Because they've got that nice little formula. Everything else is built off that idea of a 2 by 2. So let's say we want to find the determinant of this matrix. What that definition is saying is that it's going to be, if we go across that top column, and we'll talk about how we can change that in a minute, but if we go across that top column, it's going to be that first entry, which is going to be 1, times the cofactor that corresponds to the entry in the first row, first column. And then it's going to be 2 times the cofactor that corresponds to the first row, second column, plus 3. So this guy keeps going, right? So now we're here. Times the cofactor in the first row, third column. So that's what the definition is saying. Now, practically, here's what's going on. So we've got 1, right? So if I take out that first row and that first column, the minor is going to be this 5, 6, 8, 9. So the cofactor includes the sign. So this is going to be negative 1. This is first row, first column, times the minor that's left over. And then we're going to have that 2. So now we're going to, we're expanding here. So we're going to take that 2 out. So we have negative 1 to the 1 plus 2. And the minor that's left over is 4, 6, 7, 9. Plus 3 times negative 1. Now we're taking the 3 out. We gotta take the 3 out across and down. That is in the first row, third column. The minor is what's left over, 4, 5, 7, 8. So this is where we get to do some fancy math. So we're going to have 1 times negative 1 squared, which is a positive 1. So it's just going to be whatever this is. We're going to have a 1 times negative 1 cubed. Sorry, 2 times a negative 1 cubed, which is going to be a negative 2 times this determinant. plus 3 times negative 1 to the 4th. That's going to be a positive 1, so this is going to be a positive 3 times this determinant. Now, in the end, your determinant will always be a number. So our goal is to get down to that number. So let's do some math here. So we've got 5 times 9, which is 45, minus 6 times 8 is 48, minus 2 times this determinant. 9 times 4 is 36, minus 6 times 7 is 42, plus 3 times that last determinant. So 4 times 8 is 20. Just kidding. 4 times 8 is 32. Minus 7 times 5 is 35. So we have negative 3 minus 2 times negative 6 plus 3 times negative 3. So negative 3 plus 12 minus 9 is going to be 0. So then in this case, our final answer is 0. Now, we said before, and we kind of mentioned this in inverses, that determinant is kind of important because what's going to happen is that if the determinant is equal to 0, it turns out that the matrix is singular. And singular, if you recall, means no inverse, which means it's not invertible. And in this case, that determinant was 0, which means that the matrix is a singular matrix. So there's no inverse for this matrix. If you were to try to plug that in the calculator and do and find the inverse, it'll give you an error. It'll tell you that it's a singular matrix. And we'll talk about other uses as we go through this chapter on determinants. So sometimes we have to do what's called an expansion, a cofactor expansion. And that's actually what we did on that 3x3 just a few minutes ago. Now, if you remember, 3x3s have a shortcut that we could use too. There is no shortcut for a 4x4 or a 5x5, but there is a shortcut for a 3x3. So before we go on to talk about matrices that are bigger, let's go ahead and review that. And this is something you may have talked about in 172 in a trig class. So there was our matrix that we just did. Now we did it by cofactor expansion. We went along the top row. It's going to turn out you can go across any row or any column, down any column, and you'll get the same value for the determinant. But the shortcut allowed you to recopy the first two columns. And then you started multiplying down the columns. So if I multiply down this column, 1 times 5 times 9 is 45. If I multiply here, 2 times 6 times 7 . And if I multiply here, 3 times 4 times 8. So I went down from left to right. Now I have to subtract, and then I have to go the other way. So I'm going right to left now. So 2 times 4 times 9. Notice I'm still adding. 1 times 6 times 8. 3 times 5 times 7. So if I were to add 45 plus 84 plus 96, I get 225. And if I add 72 plus 48 plus 105, I also get 225. And 225 minus 225 is 0. So the 3x3s are nice because there is a shortcut method. It doesn't matter to me if you want to do expansion or if you want to do the shortcut. You'll get the same answer either way. So I wanted to review that shortcut with you. So we've talked about cofactor expansion. Now I just want to do a few, and then we'll come back to talk about triangular matrices. So let's look at 14. We have the matrix -1, 0, 2, 1, and I'm going to find the determinant. So notice I'm changing that notation there. That lets me know that I need to take the determinant of whatever's inside. So since this is a 2x2, we're just going to multiply down the diagonal. So we have -1 times 1, which is -1. Subtract, then multiply by the other diagonal. 2 times 0 is 0. So our answer will be a -1. Now let's look at 20. We have 2, -1, 3, 1, 4, 4, 1, 0, 2. So we've got a couple of ways to do this. I'm actually going to work this one a couple of ways. We could use that shortcut method. That would be fine. But I want to really practice that cofactor expansion method. So what's kind of cool is we could go across the top like we did before. So let's do that. Let's go across the top here. So if I take out that first row and that first column, it crosses at 2. It's always going to be -1 to some power. This is taking out first row, first column. So it's 1 plus 1 is the power. What's left over is 4402. And then we're going to move on to that next entry. So it's going to be plus. We've got -1 as that entry right here. And then we have -1 to a power. Now we took out the first row and the second column. What's left over is this. Plus. And then we're going to finish that. Notice we're going across that first row. So there's 3. That's where we take out that row and that column. So -1 to a power. This is in the first row, third column. What's left over is 1410. So there's our cofactor expansion. This is called expanding along the first row. So let's simplify. We have -1 to the 1 plus 1. -1 squared is a positive 1. So 2 times +1 is just 2. Here's that. This is a -1 times a -1 cubed, which will be a positive 1. This is 3 times a -1 to the 4th. -1 to the 4th is positive. So this is a positive 3. Simplify. So this is 8 minus 0. 2 minus 4. 1 minus 4. Just kidding. 0 minus 4. So this is 2 times 8 plus -2 plus 3 times -4. Order of operations. So 16 minus 2 minus 12 is a positive 2. Now with this one, notice we have a 0 right here. We didn't have to expand along that first row. We could have cut the work a little bit by expanding along the bottom row. And what's kind of cool is it doesn't matter which row or column you expand across, you'll get the same answer regardless. So let's say we saw that 0 and we said, I'm not going to go along that first. That's going to be too much work. I'm going to expand along third row. So it works, the algorithm works the same way. So if I go along that third row, so I'm taking out that third row first column, they cross at 1. And this negative 1 to a power, that's the third row first column. The minor that's left over is this. And then you move to that second entry, but what's nice about zeros is it's going to take everything out. Let's check this out. So there's your 0. That's where that row and column cross. It's negative 1 to a power. Third row, second column. What's left over? 2, 3, 1, 4. And then third row, third column. Cross at 2. Negative 1, third row, third column. What's left over? So now let's examine this a little bit closer. Notice it doesn't look anything like what's above, but that's okay. The final answer is going to be the same. It's not how it looks, it's what you get. And if you notice, 0 times a negative 1 to the 5th power times a determinant. 0 times anything is 0, right? So we don't even have to compute anything there because we know that's going to be 0. So it's already cut our work by a little bit. So let's simplify. We have 1 times negative 1 to the 4th, which is going to be a positive 1, times that matrix here, or the determinant of that matrix. This guy's going to be 0. And then we have 2 times negative 1 to the 6th. Negative 1 to the 6th is positive. So this is going to be plus 2 times this. So we have negative 4 minus 12 here. Plus 2 times, this is 8 minus negative 1. Negative 16 plus 2 times 9. So negative 16 plus 18 gives us a 2. So we're going to get the same answer that we got above, just using a different expansion. Now we can, like I said, we can expand along any column or any row. We expanded along the first row and got 2. We expanded along the third row and got 2. Let me show you what a column expansion looks like. So with this one, we could have said, oh look, I've got a 0 here in this column. So I could go down this column and use the negative 1, 4, and 0 as those entries here. So let me show you what that would look like. So we're going to take that to the next page. I'm just going to recopy my matrix. And now I'm going to show you the expansion along the second column. So if I'm going along that second column, I'm going to have a negative 1 here. It's always going to be negative 1 to a power. That is the second column, first row. Or you could say first row, second column. Addition's commutative. The minor that's left over is 1, 4, and 1, 2. So now, I'm still going down that column, but now I'm taking out that row. So I'm going to have a 4 here. Times negative 1, second row, second column. Minor is this. And then when I take out that last entry in that row, that's where my 0 is. And like we said before, 0 times anything is still a 0. So we're going to have -1 times -1 cubed, which is a +1. 4 times -1 to the 4th is a +4. And then 0 times anything is 0. So let's work this guy out. And you can see how we're getting the same answer either way. So there's lots of different options when you talk about expansion. So we've really talked about 2x2s and 3x3s. In the next video, we're going to talk about what happens if we have a 4x4, and then we're going to talk about the determinant of triangular matrices.